All right, everyone. So welcome back um, to, I guess, week 2 of internet presentations. So we have 8 total topics remaining. We have 3 more to do on applications for derivatives. Then we're going to do 3 presentations on ways of undoing derivatives. And then the last 2 are really bonus presentations. They don't officially show up in Calc 1, but they're more as a prelude to Calc 2. So it's 2 different techniques that you're going to see and use a lot of in Calc 2. So I thought that I would go and give you kind of an introduction to Calc 2 so you could know what to expect and be a little bit ahead of the game whenever you get to Calc 2. Okay, so these next 2 are going to be probably short, but we'll combine them and call them a week. So what we're going to do is we're going to suppose that we have some function little f of x. We're going to assume that our function little f is differentiable on some interval around a, and what we'd like to do is approximate little f by some function big F of x. And then we might ask, what properties would we like our approximating function to have? Well, if we're concerned about what's happening with little f at a, we would like our approximating function big F to at least have the same value as little f at a. So we want little f of a to be big F of a. And depending on what else we want, we might want the derivative of f at a to match with big F of a. So what we could do is we could define this linear approximation, so we'll call it big L of x, and if we want to get the derivative and the value of the function to match at a, we'll define L to be f prime of a times x minus a plus f of a. Now, you might recognize that this is just the tangent line expression that we've seen a fair bit at this point. And again, that makes a lot of sense because what we've said is we want the value of the function and the approximation to match at a, and we also want them to share the same derivative. And we said that those were 2 properties of the tangent line. When you go on to Calc 2, you might want more things to match. So you might want maybe the second derivative or the third derivative to also match. And there are ways of doing that, and you will see this when you go off to Calc 2. So what we're going to do is we're going to use this linear approximation to go and approximate a few numeric values. So the main idea with doing a linear approximation is it's something like you want to approximate some numeric value, but you don't have a calculator to do it. So maybe imagine that I ask, in the first example, I ask you to come up with an approximation for the square root of 1.1, but I take your calculator and I break it over my knee. Well, so what you would want to do is work around some value that you know something about, and then get a tangent line around there, and we'll see how this works. So in general, the main idea is that we're trying to approximate the black curve little f of x by the magenta line big L of x. So if we take the black curve and we start at some point a, we get an a f of a pairing, and as we move along the x-axis, we get some other point on our black curve x f of x. And the difference in these y values is just f of x minus f of a. Then we have this approximating line magenta, or we have the approximating magenta line big L of x. So that, if we go over to x, our L of x value is going to be f prime of a times delta x. So just the rise over, nicely rises over runs because we have a straight line. So there, the change in the y values for the for L of x is just this f prime of a times delta x. But what we see is that as we pick an x value, or we pick a delta x value that is going to be small, so we pick an x value that's going to be close to a, we see that the black line and the magenta line are very, very close together as we're closer and closer to a. So what this says is that for reasonably close values of x, the change in y values is approximately this f prime of a times delta x, and that's kind of the main idea. So we can take advantage of a tangent line to go and approximate a function in a close neighborhood. Okay, so first, suppose we want to find the linear approximation to f of x equals the square root of x plus 1 around the value x equals 0, and then approximate the value of square root of 1.1. So the first thing that we'll do is we'll take a to be 0, and then we'll find our tangent line around a equals 0. So from our chain rule, we'd go and get that the derivative for square root of x plus 1 is 1 over 2 square root of x plus 1. We'll then go and start setting up our tangent line equation. So L of x equals f prime of a times x minus a plus f of a. Evaluate our derivative at 0, evaluate our function at 0. We get 1 over 2 times x minus 0 plus the square root of 1. So we get that our tangent line to square root of x plus 1 at 0 is going to be x over 2 plus 1. And then we want to use this expression to approximate the square root of 1.1. Now, one mistake that might be made is just say, well, we want to approximate the square root of 1.1, we'll take x equals 1.1. But if we did that, that wouldn't be correct, because remember what we've said is that L of x is approximating f of x. So what we're really asking is, what is the x value so that f of x gives me the thing that we're trying to approximate? So in this case, if we took f of 1.1, we would be looking at the square root of 1.1 plus 1, or the square root of 2.1, which is not what we want to approximate. But if we take f of 0.1, we get the square root of 0.1 plus 1, which is the square root of 1.1. So we'll look at L of 0.1, which is going to approximate the square root of 1.1. And here what we get is 0.1 over 2 plus 1, which is exactly 1.05, or 21 over 20. And what we see is that the square root of 1.1 is just under that, so about 1.0488. So one other rule of thumb when working on these kind of questions is that if you get an approximating value that is, say, sizably different from the actual value, maybe you want to go back and check your work. So you might have done something wrong. In this case, if you'd taken L of 1.1, you would get that that value would be about 1.5, which would be a fair bit away from 1.04, which would say you probably want to go back and just make sure you've done everything correctly. Okay, for our second example. So now suppose that we want to find the linear approximation for g of t equals 1 over t at t equals 5. And then we'll use this to approximate 1/7. So as before, we'll go and find our tangent line expression around 5. So we'd get that g prime of t is minus 1 over t squared. We'll then go and set up our tangent line equation. So L of t is going to be g prime of a, where a is going to be 5, times t minus a plus g of a. So going and putting in our derivative and our function value, and then going and evaluating everything, we get minus t over 25 plus 2/5. So here we would again ask is, what is the value of t that we need to take so that g of this t value is the thing we want to approximate? Well, we need to take t to equal 7. That way g of t will give us 1 over 7. So L of t, or L of 7, will be approximately g of 7. So L of 7 is going to be minus 7 over 25 plus 2 over 5, which is 0.12. And 1/7 is approximately 0.143. So again, we come up with an answer that's pretty close to the actual answer, which is a good thing. Okay, and then the last of these examples for the linear approximation is we'd like to go and approximate sine of x around x equals 0. So again, we'll go and set up our tangent line expression around 0. The derivative of sine is cosine. So L of x will give us h prime of a, so cosine of a, times x minus a plus sine of a, where a is going to be 0. So our linear approximation is going to be cosine of 0 times x minus 0 plus sine of 0, which is just x. So what this says is that the linear approximation for sine for small angles, so something around 0, is just x. And for anyone who's done some physics, this is probably something that you're familiar with, but maybe not exactly why. And if you remember, one of the things we said a while ago is that we could write sine as an infinite degreed polynomial. the first term is, the constant term is 0, the next term is x, and then you have 0 for the quadratic term, and so on. So if you were to just take the constant and linear terms in this infinitely long polynomial, you would get just the value x. Okay, so then the next thing that we want to talk about are what are called differentials. So we're going to do the same kind of thing. So what we're saying is that we have some function f of x, and we're going to assume it's differentiable at some point a. Then what we're saying is that if we take f at our point a and we go over some distance delta x, we can approximate that. We can approximate this new value by f of a plus f prime of a delta x. So basically just referring back to the picture that we had from a moment ago. And equivalently, what we can say is that the change in the y values, so f of a plus delta x minus f of a, is approximately our derivative evaluated at a, so this f prime of a, times delta x. So just changing the notation from the Newton notation over to the Leibniz notation. Okay, so let's see how this works in general with a couple of examples. So what we're asking here is, what is the worst case error we could wind up with for the area of a square with side lengths measured to be 5 centimeters and a measurement error of 0.1 centimeters? So pictorially what we have is this. We have a square, we have side lengths of u, but we could be off. We could be off by as much as delta u, either the positive or the negative direction. For this, I'm going to go and draw the positive direction just because it's a little bit easier to draw and refer back to. If we did the negative side, the same kind of idea all holds, but we just would have a little bit more to talk about. So the idea with this is that we have this original area. And then we could ask, well, what's the worst possible case that we could be off? Well, the worst possible case that we'd be off is the area of this entire dashed rectangle. And we'd have 3 pieces that we would have as extra. So um, we'd have this segment up top that has height delta u and length u. We would then have this other long segment that has height u and length delta u. And then we'd have this third part of the square, which would be a small square with side lengths delta u. So over here we would get u times delta u. This other segment we would get u times delta u, and then the third part we'd get a delta u squared. So the worst case that our error, or that our area could be off by, is 2 times u times delta u plus a delta u squared. Okay, so from going back to this, we can approximate the area by finding the derivative, evaluating at, in this case, our side length, or evaluating at the given side length, and then multiplying in by the error. So for illustrative purposes, we have our area for a square. Area as a function of the side length is just s squared. So from that expression, what it says is that the worst case that we could have in the area, so the change in the area at its worst case, is approximately twice the side length times the change in the side length, which is twice 5 centimeters times 0.1 centimeters, or 1 square centimeter. So if we come back to this, what we'd said is that our change in the area is exactly our u times delta u plus our other u times delta u plus our delta u times delta u. And when we add all of that up, we get the 2 times 5 centimeters times 0.1 centimeters plus 100th of a square centimeter. So what we're really saying is that this piece up here, compared to the area from these other 2 pieces, is very small, and we're just going to casually ignore it. So the exact change in the area is 1.01 square centimeters. We approximated the change in the area to be 1 square centimeter, and for sake of argument, 1 square centimeter is pretty close to 1.01 square centimeters. So what we've done to approximate the worst case area is pretty good. Okay, then our second example. So same kind of setup. We would like to ask, how does the volume of a snowball change as the radius drops from 5 centimeters down to 4.92 centimeters. So we know that the volume for a sphere of radius r is given by 4/3 pi r cubed. And from this expression, we can find the change in volume to approximately be the derivative times the change in the radius. So our derivative of the volume is going to be 4 pi r squared. And then we still have our dr kicking around. So what that says is that the approximate change in the volume is going to be 4 pi times 5 centimeters squared times minus 0.08 centimeters, or minus roughly 25 cubic centimeters. Now, if we wanted to find the exact change in the volume just to compare this, we would have to find the volume of the radius plus our change in radius. So that would be the volume for a radius of 4.92 centimeters, and then subtract off the initial volume. So subtract off the volume of the sphere with 5 centimeters. So if we did that, what we'd wind up with is just two different expressions for volume. So we'd have the volume for a sphere of radius r plus dr, and then subtract off the volume for a sphere of radius r. If we take this r plus dr cubed and we expand everything out, we would wind up with this whole expression, and then just plug in our r and our delta r. The first thing that we can notice in this is that the original volume, the 4/3 pi r cubed, cancels off with one of the terms in this expansion. And what we get for an exact change in the volume is 4 pi times 5 centimeters cubed times minus 0.08 centimeters plus some extra terms. And what we see is that really we're doing a lot of work and we're not changing things that much. And the reason is basically this. So we're saying, what we'd assume is that for whatever our measurement is, in this case 5 centimeters, the change in the radius is not going to be that big comparatively. So we have 5 centimeters and 0.08 centimeters. 0.08 centimeters is kind of small compared to 5 centimeters. Well, if 0.08 is small compared to 5, the next term is going to have a 0.08 squared, which is going to be very, very small compared to 5. The next term that we have is a 0.08 cubed, which is very, very, very small. So effectively what we're doing is we're just saying, we can ignore these two terms that are going to change things a little bit, but not that much. So again, what we'd have is, if we just ignored these two terms that are kind of small but change things a little bit, we get exactly what we started with. So we get our derivative times our change in the radius in this case. Okay, so then the last thing that we can do is talk about a couple of kinds of errors. So suppose that we have some function that we're concerned with f, and we approximate it by some other function L at some given point x. Well, the first thing that we could do to measure our error is just go and look at the difference in the two values. So take the absolute value of f minus L and see what that comes out to. Well, that's great. So say we get an f minus L and the answer we get is 1,000,000. Well, is that something good or bad? Well, it depends on what you're doing. For example, if you were doing something that was looking at, I don't know, the net worth of Jeff Bezos, if you're off by 1,000,000, comparatively speaking, that's not really anything concerning, because you're looking at something where f and L are going to be on the order of billions or tens of billions. If you're looking at something like I don't know, maybe a city government, maybe being off by 1,000,000 is not a good thing. In the same way, if you were off by 1, if you were doing something where you needed precision down to the second decimal place, being off by 1 is horrible. But in other contexts, being off by 1 isn't that bad, which raises the next kind of error, which is the relative error. So the relative error just takes the absolute error and it divides out by the exact value. So this gives you kind of an idea of scale. So for example, if we were looking at something where f was in the order of tens of billions and the absolute value of f minus L was about 1,000,000, we'd be looking at something where it's 1,000,000 divided by 10 billion, so 1 over 10,000 roughly, which would be quite good. And then we could go and give the percent error, which is just taking the relative error and multiplying it by 100%. So if you had something like 1,000,000 divided by 10 billion, you would get 0.01%, which is quite good for an error. And then the last kind of error that you'd wind up with is what's called the propagated error, and that's just the delta y is given by the delta y is the exact change in the f values, so f of x plus delta x minus f of x, and that's approximately f prime times dx, so just what we had from the page before. Okay, so one final example here. So if we're given the measurement of the radius for some ball bearing to be 0.7 centimeters, and we're told that the measurement is correct to within 1/10 of a centimeter, so not a great measurement offhand, so we would expect our errors to not be great in this case. What we would like to do is go about finding an estimate for the propagated error, so just doing what we did a moment ago, and also find the relative error for our volume. Okay, so if we do that, we'll set things up just like we did a moment ago. So we'll say that we have the volume of a sphere, 4/3 times pi r cubed. Our derivative is then 4 times pi times r squared. So just continuing as we had a moment ago, we could say that our change in the volume is approximately v prime of r times dr. So 4 times pi times 0.7 centimeters squared times 0.1 centimeters. So our radius of 0.7 and our change in radius of 0.1. So it would say that our volume is off in the worst case by about 0.6 cubic centimeters. So again, that gives us a number, but it doesn't have any necessary, it doesn't exactly have any context to it, because maybe we're not exactly sure how good of an error that is. In some contexts, 0.6 centimeters cubed might be very good, in other ones not very. Okay, so then we go and we look at the relative error. So just what we had here, our relative error is approximately df, or in our case dv, divided by the v. So for us, we said that dv over v we'll say is v prime of r times dr, all divided by v of r. And if we go and we put in our two expressions, we get 4 pi times r squared times dr, and we divide the entire thing by 4/3 pi r cubed. And canceling off a couple of pieces, we could cancel off some 4's, we could cancel off pi's, and we could copy off 2r's, cancel off 2r's in the numerator and 2r's in the denominator, and then flip the 3 up into the numerator. We get 3 times dr over r, which is going to give us 3 times 0.1 centimeters divided by 0.7 centimeters. Our units will cancel away, which is also something that you want to make sure happens. And we get approximately 0.42, or 42% error. 42% error is quite horrible, but maybe that's kind of what we would expect, because in looking at this, the measurement error is not that good. Okay, so that's about everything that we need to say for linear approximations. Again, if you have any questions, please don't hesitate to send me an email or anything. I'll probably do another Zoom session at least sometime in the next week. And if you have any questions, let me know. I'll go and put another quiz up on Friday, some questions over this topic and some other questions over the next topic. Okay, and I will see you all then.